Hi, everybody. It's Professor Mitchell, and today we're talking about section 7.5 on indeterminate forms and L'Hopital's rule. L'Hopital's rule is a method for finding limits. Just to give you a little bit of interesting historical background on L'Hopital's rule. L'Hopital's rule was discovered by a mathematician named Johann Bernoulli. It was not discovered by L'Hopital. Now, the Bernoullis were a brilliant mathematical family, but they were not especially nice people. And the reason that this rule is called L'Hopital's rule is because the mathematician L'Hopital, who has sadly been forgotten mostly, except for this one rule, wrote to Johann Bernoulli to ask for help with the problem that this rule solves. And Johann Bernoulli wrote back to him with the solution. And L'Hopital was writing a calculus book. And L'Hopital was so considerate about the idea of not taking credit for somebody else's work that not only did he give Bernoulli credit for the one small section on L'Hopital's rule, but he published the whole entire book anonymously. And nevertheless, Johann Bernoulli got very upset with him and accused him of plagiarism. And I'm not exactly sure what happened after that. But anyway, the rule today is called L'Hopital's rule. So I like to think that that's a nice little bit of karma. All right. So as you hopefully remember from Calc 1, finding limits, there are various methods for finding limits, and many of the examples that you've seen before, you have to do some sort of algebraic trickery because, of course, the very first thing you try to do when you evaluate a limit is to just plug in the number. And once in a while, especially when you're first learning limits, that actually gives you the answer, the value of the limit. But on about the second day that you're working on limits, just about all of them originally evaluate to this form, 0 over 0, or possibly some other indeterminate form. And you have to do something else. So for example, here is a classic type of limit problem from early Calc 1. I'm going to switch over to my tablet just briefly to remind you how we did these in Calc 1. All right, so of course, the first thing I try to do is substitute, substitute x equals 2. And when I try to substitute x equals 2, here, let me start practicing what I'm going to ask you to do when you do limit problems. The numerator evaluates to 0 and the denominator also evaluates to 0. So what I would like you to say in this case, especially when you start using L'Hopital's rule, is something like this. Please, please, please do not write equals 0 over 0. I will get very upset with that, and I will probably ding you at least a point. There is no such thing as equals 0 over 0. 0 over 0 is undefined, okay? But it is a type of indeterminate form. So what we did in Calc 1 was we would factor the numerator and denominator like this. Let's see, denominator factors into x minus 2, x minus 3. And now, in the definition of limit, it specifies that the value of a limit has nothing to do with the value of the expression at, in this case, x equals 2. So you have to be careful when you do this kind of thing, because technically that's only true if x does not equal 2. And since we're looking at the limit as x approaches 2, we know that x does not equal 2. So now we get that this limit is equal to the limit as x approaches 2 of x plus 2 over x minus 3 which I can now evaluate by substitution. That comes out to 4 over -1, which is -4. All right, so that's one type of situation that you see in Calc 1. And then another, a personal favorite of mine, possibly not of yours, is this: the limit as theta approaches 0 of sine theta over theta. This limit actually forms the basis for all of the calculus that we do with our trigonometric functions. For example, the fact that the derivative of sine theta is cosine theta depends on the value of this limit. And I am not going to talk you through the whole explanation of why this limit is what it is, but I am going to put it up on the screen. And if you're interested in remembering how that works, why, you can pause the video and look this over for a minute or two. It's because of the squeeze theorem or the sandwich theorem. And this limit, as you see down here, is equal to 1. All right. So what does L'Hopital's rule say? Well, suppose that f of a and g of a are both equal to 0, and that f and g are differentiable on an open interval I containing a, and that g prime of x does not equal 0 in this interval, except possibly where x equals a. Then the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x, assuming that that second limit exists. So this is actually kind of amazing. What it says is that when you're trying to evaluate a limit, and this would work on both of the two examples that we just looked at, I'm going to show that to you in a second, and you get the form 0 over 0, that all you have to do is differentiate the top and differentiate the bottom, and then try again. And if it works the second time, then that answer is also the answer to the original limit. Now, one word of caution: I have seen a handful of students do this over the years. Please notice that this is not the quotient rule for finding the derivative of f of x over g of x. I like to say it's what you wish the quotient rule was, which is just differentiate the top and differentiate the bottom. All right. Okay, so let's, and I am going to spare you the proof of this. It turns out the proof is not terribly complicated, but as I said in the beginning, I'm going to resist the urge to prove things whenever I can, and I am not especially dying to do this proof. So this is one that we can skip. Okay, so here are the two examples we just looked at. Now, let me say this. I appreciate when students, if you're able to find the limit some other way, I appreciate if you find it some other way. All right. For example, if you remember the Calc 1 method, L'Hopital's rule to me is sort of a gimmick. It is a shortcut. I mean, it's a perfectly fine shortcut, but what I like about doing it the Calc 1 way is that it's kind of easier to understand what you're doing and why it works. Anyway, having said that, I really want to show you these two just to convince you that it does work, at least for these two examples. So again, if I try to plug in 2, I get the form 0 over 0. So by L'Hopital's rule, and I don't know where I got into this habit, I usually put a little L'(H) when I am using L'Hopital's rule. You don't absolutely have to do that. I'm going to differentiate the top. The derivative of x squared minus 4 is 2x. And differentiate the bottom. The derivative of x squared minus 5x plus 6 is 2x minus 5. And now I'll try again. 2 times 2 is 4. 2 times 2 minus 5 is -1. Oh my gosh, look at that. It's like magic. Okay, gives me the same answer we got before. And if I tried it with this second one, and by the way, whenever you run into limit as theta approaches 0, sine theta over theta, you can just tell me that's 1. I really don't need to see your work. I will assume that your Calc 1 instructor walked you through that proof when you took Calc 1. At least I hope they did. I certainly would have, all right, if I had been your Calc 1 instructor. So using L'Hopital's rule, the derivative of sine theta is cosine theta, and the derivative of theta is 1. And now substituting theta equals 0, you get 1 over 1, which is 1. It's like magic. All right, now, of course, we're not going to use L'Hopital's rule for a bunch of limits that we already know how to do some other way. So let's get into a few that probably would have stumped you if you had seen them in Calc 1. I think it's just these. Oh boy, hold on. There we go. My computer has been a little glitchy. All right, switching over to the tablet. Our first example is the limit as x approaches 0 of sine x subtract x over x cubed. So the first thing that you absolutely have to do, and this is very important, by the way, because if substituting the number in would just give you the answer right away, then applying L'Hopital's rule will actually change the answer. So it is incorrect to use L'Hopital's rule for now, unless it's the form 0 over 0. You can use it with some other forms. We'll talk about that in just a little bit. But if you plugged in 0 and you got 4 divided by 2, then the answer would be 4 divided by 2. You would not use L'Hopital's rule. All right, but now I am going to use L'Hopital's rule because this is of the form 0 over 0. Okay, so taking the derivative of the top, I get cosine x subtract 1. And the bottom, I get 3x squared. And now I try again. The cosine of 0 is 1. 1 minus 1 is 0. And 3 times 0 squared is 0. Uh-oh. Still 0 over 0. Well, guess what? Because it has the form 0 over 0, then you can apply L'Hopital's rule to this limit, all right? Basically, you just keep trying until you get something that's not 0 over 0. All right, so let's try it again. The derivative of cosine x is negative sine x. And the derivative of 3x squared is 6x. Okay, now this limit also has the form 0 over 0, but you know what? I'm going to practice what I preach. And instead of using L'Hopital's rule again, I'm just going to point out to you that you can pull a negative 1/6 out front here, which leaves you with our old friend sine x over x as x approaches 0. So instead of using L'Hopital's rule again, I'll just point out that I already know that limit is 1. And therefore, this limit comes out to negative 1/6. So again, if you know how to find the limit some other way, then try to find it some other way. All right, only use L'Hopital's rule if you're kind of desperate. Okay, and then the other example was the limit as x approaches pi over 2 of natural log cosecant x over the square of x minus pi over 2. Okay, so checking the form. The cosecant of pi over 2 is the reciprocal of sine pi over 2. Sine pi over 2 is 1. So the reciprocal of 1 is 1. The natural log of 1 is 0. And pi over 2 minus pi over 2 is 0. The square of 0 is 0. So this has the form 0 over 0. So using L'Hopital's rule, the derivative of natural log cosecant x, that's a relatively new derivative rule that we just learned recently, would be 1 over the cosecant of x times the derivative of cosecant x, which is negative cosecant x cotangent x, right? And then the derivative of x minus pi over 2 squared is 2 times x minus pi over 2 times the derivative of x minus pi over 2, which is 1. All right, so what do we have here? Well, the cosecant x's drop out. And the cotangent of pi over 2 is the cosine of pi over 2 divided by sine pi over 2, which is 0 over 1. So this is still 0 over 0, or it has that form. All right, I don't want to say it is. So let's use L'Hopital's rule again. I think one more time is going to do it. All right, so now we have the derivative of negative cotangent x. Well, the derivative of cotangent x is negative cosecant squared x. So that negative that's already there will cancel out the negative in the derivative formula and just leave me cosecant squared x. And then the derivative of 2 times x minus pi over 2 is just 2, right? So now I think we can do it. As we said earlier, the cosecant of pi over 2 is 1. 1 squared over 2 comes out to 1/2. All right, so that brings us to some other indeterminate forms, namely indeterminate forms infinity over infinity, infinity times 0, and infinity minus infinity. By the way, what it means for a form to be indeterminate is that when you try plugging in the number to evaluate the limit, not only does that not work, but it doesn't give you any information about what the value of the limit is. So to give you an example of a form that is not indeterminate, infinity times infinity is not indeterminate, because when you take a really big number and multiply it by a really big number, you get an even bigger number, right? So that limit would be infinite. Infinity divided by infinity is indeterminate, because when you take a really big number and divide it by a really big number, well, you can kind of get any kind of number. It depends on, exactly how big those numbers are, especially relative to each other. All right, so starting with infinity over infinity, it turns out that L'Hopital's rule still works exactly the way that we were using it before. So if you plug in the number and the top and the bottom are both approaching infinity as x approaches a, then you can take the derivative of the top and the derivative of the bottom and then try again. So we'll use this example to show how that works, although this is a Calc 1 limit, as I will point out to you here in just a second. All right, so I'm sure that in Calc 1, you learned, and my experience has shown me that students tend to learn 2 different versions of this. You either learned the trick for actually evaluating this limit, which is to divide every term by the largest power of x that appears in the denominator, which would be x squared. And then when you let x tend toward infinity, you can find the value of this limit. Now, there is a shortcut. And what I used to do when I taught Calc 1, it's been a few years now, is I would actually make a special homework problem out of sort of proving that this shortcut works. And the shortcut is basically to just take the leading coefficient of the numerator, which is -8, and the leading coefficient of the denominator, which is 12. And this limit turns out to be -8/12, which simplifies to -2/3. Okay, but I do want to show you that L'Hopital's rule also works on this. So if you imagine x getting bigger and bigger and bigger, then what's going to happen is that this term here is going to dominate and is going to make the whole numerator tend towards -infinity. And then the denominator, as x tends toward infinity, both of those terms are tending towards positive infinity. And so the denominator is tending toward positive infinity. So this limit has the form, I could say -∞/infinity, but we usually don't bother with the negative. The negative doesn't matter for the form. Okay, so using L'Hopital's rule, the derivative of x minus 8x squared is 1 minus 16x. And the derivative of 12x squared plus 5x is 24x plus 5. So now if we try again, the dominant terms in the numerator and denominator are -16x and 24x, respectively. So this is still tending towards -∞/infinity, which we will just call infinity/infinity. So we apply L'Hopital's rule one more time. And by the way, this would be another good example of a problem that I would say, hey, you really don't need L'Hopital's rule for this one. I like it as an example here because it's sort of convincing you that L'Hopital's rule works. It's making the limit what we think it should be. The derivative of 1 minus 16x is -16. The derivative of 24x plus 5 is 24. And -16/24 still simplifies to -2/3. Woohoo! All right. Now, back to the presentation. I'm going to try to make it so that my other windows don't randomly pop up. Oh, darn, I forgot about this one. I would have put this one up before. Forgot that I had two examples. So this is one that, we didn't learn how to do in Calc 1. In Calc 1, we didn't even know what log base 2 was or really anything about it. As x tends toward infinity, log base 2 of x also tends toward infinity, and so does log base 2 of x plus 3. So this does have the form infinity/infinity. Using L'Hopital's rule, let's see if we remember what the derivative of log base 2 of x is. If you don't remember and you can't find it in your notes, you could always use the change of base formula to write it in terms of natural log x. But actually, the derivative of log base 2 of x is 1 over x natural log 2. And the derivative of log base 2 of x plus 3 is 1 over x plus 3 times natural log 2 times the derivative of x plus 3, which is 1. All right, so now I'm not going to try anything with this just yet. I am going to rewrite this because I think that we will actually be able to solve this now. So can't we just flip this around so that it's x plus 3 natural log 2 divided by x natural log 2? And then the natural log 2's cancel. Okay, and I could use L'Hopital's rule on this, but actually I think I know a better way to do it. Instead of writing that as x plus 3 all over x, why don't we just write it as x over x, which is 1, plus 3 over x. And then as x tends toward infinity, 3 over x tends toward 0, and this limit is equal to 1. All right. Okay, now back to the presentation, because I'm pretty sure that that was my last example for infinity over infinity.